Assalamu alaikum, dear students. This is your deformation chapter, and the lecture number is lecture 3 of this particular chapter. Before this discussion, we have already discussed in the previous two lectures about the young modulus and how we can calculate the young modulus, and of course what experiment we can do for young modulus, what is Hooke's law, and how we can write Hooke's law in terms of forces and in terms of your stress and strain. So all these discussions we had before this lecture. Today, as I said, that we are going to discuss the particularly the situation of the elastic energy. And before going to detail of elastic energy, first of all we have to recall what is elasticity. So simply we can define elasticity in this way, that the elasticity of a body is its ability to return to its original form after the distorting forces have been removed. Yani if you have a situation like a spring attached with a weight, and of course the weight is giving a sort of extension, but when you will remove this weight, what will be the situation of this spring? So if the spring is going back to its original length, suppose this was the original length, so if the spring is going back to its original length after the removal of this weight, this was the length after the extension, and when we were hanging weight with the spring. So what we are saying, when we are removing this weight, if the body is going back to its original shape, then we have a good ability of restoring its original shape after the removal of the weight or load. So this is basically the ability of a body, and this ability will be the elasticity, or the how elastic your body is. You can simply say that if the body is going back to its original length after the removal of the weight, then the ability of that object of elasticity, you can say, or going back to its original shape after the removal of the distorting force is good. So this is the elasticity. Now if this is happening in a body, yani when you are removing the distorting forces and the body is going back to its original shape, then the situation will be of elastic deformation. Yani the deformation in the body is called as elastic deformation, and the body is of course will come as the elastic body. Elastic body. But on the other hand, if after the removal of the deformation force or deforming force, the body is not going back to its original shape, then you will say that the deformation is plastic deformation and the body is plastic body. Is it clear? You are removing, when the body returns to its original shape or form after the distorting force have been removed, the deformation is called as the elastic deformation, and the body is elastic body. When you are removing the when there is a permanent deformation in a body, even after the removal of the distorting forces, the deformation is called as the plastic deformation, and the body will be termed as the plastic body. So this is very, very important, that how we can define a plastic or elastic deformation and what is elasticity of a body. Then here you can see both these behaviors, elastic and plastic deformations, through these two graphs. Suppose you have two graphs between stress and strain. Over here you have the same, you can say, quantities, stress and strain. But what you can observe in this case, in the first case, in the first graph, you are loading the you can say suppose a spring or a string, and the line is straight, and when you are uploading or when you are deloading or removing the load, simply you can say, or unloading, then what is situation? What is the situation? The situation is that the graph is going back to its original position. Yani you are attaining zero strain when the stress is zero. So simply you can say that when the body is following Hooke's law, when uploading and unloading, the situation will be of elastic deformation. So remember this thing. Elastic deformation means that there is no final strain. The body is coming back to its original position when you have removed all, when you are increasing the strain, of course, stress, the strain is increasing. But when you are removing the strain, you are coming back to the original state, yani there is no strain in the body as well. So this will be the situation of elastic deformation. On the other hand, what you can see here, that you are deforming a body in this way, that they are not following the Hooke's law, and you can say that they are going beyond the elastic limit when you are loading the system, and when you are unloading the system, there is a permanent deformation. There is a permanent deformation, or there is a permanent strain in the body. So this permanent deformation shows that this time your body is plastic body, and the situation is plastic deformation. So remember this thing, that in case of your permanent deformation, there will be a permanent strain. Yani what you can say, that when you are unloading the system from, suppose, this point, you are unloading the system. So at this point, what will be the value of the stress? Zero. But what will be the value of the strain? This is the value you have. So you can simply say that we have a permanent deformation. So strain is here even when we have removed all the stress. So this will be the behavior of the plastic deformation. So this is very, very important. Now, if you will talk about the energy stored in a stretch wire or spring or in a deforming body, then what will be the situation? Here you have a graph between the force and extension. Extension is of course in millimeter, normally millimeter, and force is in Newton. So what is happening in this case, that we are considering the stretching without the you can say exceeding the proportionality constant. It means that we are obeying the Hooke's law. Now the point is that here at this point, suppose at the initial point force was 0, and somewhere here you have applied a force up to F2. So overall, if you will calculate the force, you will calculate the average force from 0, yani F1, to a force F2. So simple thing is that energy stored is nothing but the work done on the wire. So how you can calculate the work done on the wire? So this is simple situation, that Fe average multiply by extension. Yani work done is basically force into displacement. But in this case, what we are saying, that instead of displacement, you are using the term extension. So you can say that the average force is here, because initially the force was 0 and we have moved up to force F2. So the average force we have to consider, and this is nothing but the area under the curve. So this is all area under the curve. Remember this point, that area under the curve will always be taking towards extension side. What does this mean? You can say that sometimes the graph will be in this way, that the extension is along y-axis and force is along x-axis. So if you have a graph like suppose this, then what you will say, that the extension is towards, of course, y-axis. So this will be our area for the work done or energy stored in a body. This time what we have, as our force is along y-axis and extension is along x-axis, so this area is the area which is giving us the energy stored in a body, or simply you can say the work done on the wire. So how you are calculating this work done? Area under the graph. Mathematically what you are doing, average force multiplied by extension. And how you are calculating the average force? So simply you can say that average force is nothing but F0, F1 plus F2 divided by 2. This will be your average force, and as the F1 is 0, so simply you can say that here we have 0 plus F divided by 2. Yani F2 we are considering as F. So simply half F is your average force which you are using here. So half F into E. Is it clear? This is very, very important, that why we are taking half. So two, you can say prong explanation. One is that the average force into extension, and on the other hand you can say this area under the graph, which is nothing but the area of the triangle, and simply we can say that area of the triangle is nothing but half height and breadth. So this is how you are writing. Now you already have discussed in the first lecture that F is nothing but KE, where K is the spring constant. So F is equal to KE is giving you half KE, and 1E is already here. So half KE square. So simply you can say that here the area under the graph is nothing but half KE square, because the quantities are extension and the force. So remember this thing, that whenever you will try to find out the energy stored, what you have to do, simply either you can use half Fe as we did here, half Fe, or if you will use your value or equation for F, which is Ke, so you can write as half Ke square. So be careful of these two equations, and of course this concept of area under the curve. Now if we will write in this way, that energy, basically if you have suppose a wire, so wire will have a cross section area, as well as here you have suppose cross section area, and here you have the length of the rod or wire. So these two factors, any area of cross section and length, these two factors are also involved. So simply you can write in this way that energy is stored per unit volume. If you will write, then what you can write over here, half Fe. So what you can write, half Fe divided by volume. Yani you have basically divided both sides of the equation by volume. Now as far as the volume is concerned, you already know that volume we can calculate by the multiplication of area into length. So this will be the volume. So if we are just going other way around, yani if we have volume, what we can write, A into L. And when we have A into L, we can recall quickly that if we can write F over A and E over L, then we will have another you can say a situation, another concept, and this is nothing but your first term is nothing but F over A, which is the stress, and the second term is nothing but your strain, which you have already discussed in the previous discussions or lectures. So what you can simply write, that half into stress into strain will give you energy stored per unit volume. So remember this point, that if instead of this graph, as we have just discussed, instead of this graph, if the graph is given in this way, that you have the stress along y-axis and strain along x-axis, then the area under the curve, and if you have this situation, area under the curve, you have to consider that what is the quantity along x-axis and what is the quantity along y-axis. So if the quantity along y-axis is force and along x-axis is extension, the area under the curve is giving you energy stored in a body. But if instead of this force you have a stress yani sigma along y-axis and strain yani epsilon along x-axis, then this area under the curve will give you nothing but energy stored per unit volume, because this time, as I have explained here, the energy stored is not only energy stored, but it is energy stored per unit volume. And simply you can say that when the graph will be along the stress and strain like this, then the area under the curve, as I have drawn with pink color, this will be the energy stored per unit volume. So be careful of this explanation, and this is very, very important to understand that how we can get this area under the curve and what will be the deformation. And of course this is loading unloading situation. And if suppose here you have this situation, like you are going somewhere here, you are loading the system. So simply you can say loading the system means, if we will consider this area under the curve, overall area under the curve, this area is giving us, I'm just using suppose pink color here. So this is something which is the total work done for the deformation. Total work done for the deformation. So remember this thing, that energy per unit volume of course, but this is the total work done for the deformation. Now what is happening? You can say that when we are unloading the system, where we are unloading the system, here we are unloading the system, yani we are going back. I can draw a thick line, we are going back somewhere here. So this is the unloading. So it means that ultimately what is the situation? Situation is that we have a permanent deformation. This is the permanent deformation, and this is the permanent strain, you can say. So this curve or this part of the curve is giving us the energy which is absorbed in the system, absorbed in the spring. And you can simply say that the other part, which is suppose this part, we have recovered. So this is the recovered part of the energy, and the color which I used before is giving you the energy is still inside the body. So simply you can say here that this is the graph which is showing us the energy absorbed in the body, and somewhere here we have the energy which has been recovered. So whether you are using the force and extension graph, or you are using the stress strain graph, remember this part, the where you have the permanent extension, this part is showing you the energy absorbed in the system and not recovered, and this will be the part which you of the energy which has been recovered. And as I said that if you will draw this complete area under the curve, this will be the total work done on the system. So be careful. This is total work done on the system. Yani if you have a spring or a string or whatever is the body, I have shown with these lines the total work done. And here you can say that this is the situation, this is the area showing you the energy absorbed in the system, and we can make another line here, and this area shows the energy recovered. So this is the situation, and the number of times you will see these type of questions in your past papers. So be careful, and of course, as I have already explained, so whenever you want to calculate the energy stored, simple equation is nothing but this equation I am writing here again. Energy stored is nothing but half Fe or half Ke square. On the other hand, energy is stored per unit volume. This is nothing but half into stress into strain. So be careful when you are using stress and strain, and when you are using the force into extension or spring constant E square. So remember these two equations and you can calculate easily the results. Here again you can say and see, I have already explained actually on the other page. So if you can recall, this is the energy absorbed. This is the energy absorbed, and as we have already explained that the other part will be energy recovered. So this is your energy absorbed, and here you have the energy recovered. Both, when you will take both of these areas together, this will be the complete work done on the system. So remember, excuse me, remember this point that when you have the total energy or total work done, when you are loading the system, and when you are unloading the system, what is the situation? Yani, on the other hand, we can say another, you can say point, or we can mention another point here. Like if you have a graph which is for your material which is obeying Hooke's law completely, and for loading and uploading you have a straight line, suppose, then what will happen? Simply you can say whatever the work we will do on the system, suppose F and E over here you have. So of course when you are applying the force, yani loading the system, this is the graph which is from suppose A to B. But when you are unloading the system, you are going back to A from B, and as you can see that there is no extension, permanent extension. So whatever the work we have done on the system, complete work done has been recovered, and the total energy has been recovered, and there is no absorbed energy in this system. So you can say that in case of elastic body, total energy will be recovered, and in case of plastic body, whatever the energy we will stored in the system as a work done, a part of it will recovered and a part will be lost, you can say, in the system. So this is very very important, and number of times you will see question based on this discussion. So I hope that this lecture will be very important for you, and of course I will advise that if you want to get the total concept or complete concept of your deformation thing, then you should go for your lecture 1 and lecture 2 of this the chapter deformation of solids, and inshallah you will understand the whole you can say chapter. In the next discussion I will upload few MCQs related to the deformation thing. So be ready for the next discussion and lecture. And as I said that I will upload some MCQs based on the chapter of deformation of solids. I hope this lecture will be good for you. So if you like it, you just put the like button, and of course share this discussion with other students as well. And of course, if you are new on my channel, then subscribe this channel, and in this way you can get all the lectures and discussions which I will upload time to time. And I hope that these will be a good source of information for you. So be ready for next discussions. And of course, as exams are coming, so give more and more time to your preparations. Good luck for your success in your exam. And till the next lecture, Allah Hafiz, take care.